So it's lecture 27, I guess, the second last lecture. Oops. And before I start, I just want to make some clarification. So one thing, I mean, I really should have said an announcement. You may have noticed on Gradescope that homework 12 is due on Thursday night. So this is not an accident. It's due later. I mean, just because it was posted a little later, and just to give you some more flexibility in the end of the semester. I guess people have a lot of deadlines. So homework 12 is due on Thursday night. There will be a review session next Thursday. By me and also by the GSIs. You'll get information about that. You'll get an email with practice exams and a lot of information like that later. But okay, so let's get on with the lecture. So in this lecture, we're going to introduce one of the most useful ideas in math, I would say, which is Fourier series. And we're going to introduce it in the context of, yes?
I have one logistic question before we start.
Sure.
Is today's homework included on the Thursday's homework, or?
No. It's homework 12. It's last week, the stuff that was assigned last week. Yeah. So I'm going to talk about inner product spaces. This is section 6.7 of Lay. And then I'm going to talk about Fourier series, which is, you can think of as maybe the single most important application of this idea of inner product spaces. This is sections 10.3 and 10.4 of Nagel, Saf, and Snyder. Okay, somebody raise their hand. If it's a mathematical question, please go ahead. If it's a logistical question, I'd like to save it till the end. Okay. So let me start by talking about inner product spaces. So remember, like way back before midterm 1, we talked about Rn, and then we realized that you could abstract everything you learned about Rn, and it still worked in a general vector space. Right. So this was, I guess, this was the topic of chapter 4, and this is everything before midterm 1. And then we learned about, in chapter 6, we learned about the dot product, which came with a whole bunch of associated concepts that were very useful, namely, orthogonality. So I'll just draw perpendicular orthogonality, orthogonal basis, orthogonal projection onto a subspace. Okay, given the orthogonal projection, there are these related ideas of finding a best approximation of a vector in a subspace, or a unique decomposition of a vector. And then there was this Gram-Schmidt algorithm. And then there was the associated concept of a norm. There was all this stuff that came out of the dot product. And what we're going to do now is we're going to ask, well, is there some way to generalize this to general vector spaces, the dot product? And it turned out there is, and this is what's called an inner product space. So this is going to be like the dot product, but for general vector spaces. And we're going to follow kind of the same procedure that we did in chapter 4. We're just going to abstract the essential properties of the dot product, right? So let me tell you the definition. Maybe I'll make a new page. Here's the definition. An inner product space is a vector space with an additional structure called an inner product. So along with an inner product. And what that is that's a function, i.e. a function denoted with these angle brackets that takes two inputs. And it maps pairs of vectors to real numbers. So what that means is it takes a pair of vectors u and v in the vector space and maps them to the inner product of u and v, which is a real number. Okay, so these live in the vector space. So it's a function that takes two sorry, wait, is somebody seeing an elephant? Wait, what?
I think the function, the brackets, the dots, and the comma looks like a nose.
Oh, wow. Nice. Okay, cool. Yeah, I never realized that. Okay, yeah, good. Not bad. Okay, I hope you remember it that way. So anyway, it's a function with a bunch of properties, right? The essential properties. So satisfying 4 properties. So the inner product of u and v is the same thing as the inner product of v and u. Then the second is it's linear under addition. So u1 plus u2 inner product v is u1 inner product v plus u2 inner product v. Then again, linearity under scalar multiplication. So c times, I guess I'll call it u. Is just c times inner product of u and v. And the last property is that if you take any vector, so c is a real number here. So, and this is of course for all vectors u and v in the vector space. And the last property is if you take any vector u and take its inner product with itself, you get something that's non-negative. Okay, so these should be familiar. You've been using these properties with the dot product all along. And now we're just saying, well, any function that has these properties, we're going to call that an inner product. And once you have this, you can correspondingly define some associated notions. So correspondingly, you can define the norm of a vector u to be the square root of its inner product with itself. And that makes sense because the inner product is non-negative, right? You don't want to take a square root of a negative number. So this is always non-negative. And you can define u is orthogonal to v if the inner product is 0. So this is just completely identical to what we did for the dot product. Okay, so now we're adding the structure of chapter 6 to this arbitrary vector space. So let me show you a few examples. But before I do that, any questions about the definition?
So we haven't these are the properties an inner product has to satisfy, but we haven't really defined what an inner product is yet.
An inner product is anything that satisfies these properties.
Oh, okay.
So I'm going to give you some examples of inner products. So this is, kind of like when we define vector spaces, right? A vector space is any set with operations that satisfy these properties. Similarly, an inner product space is a vector space and a function that satisfies these properties.
Okay.
Let me show you some examples. So the most familiar example is just the dot product, right? Take V equal to Rn and take the inner product of two vectors to be just U dot V. So that's all what we already did. And that satisfies these four properties. So that's an inner product. Okay, not very new or particularly surprising. Here's another example. Let's take V equal to R3 for concreteness, and let's define the following inner product. U inner product V is U1 V1. Sorry, these are numbers, so no underline. Oops. Plus, I don't know, 2 U2 V2 plus 4 U3 V3. Okay, that's different from the dot product. But that's a legitimate function, on this vector space R3, and you can check it satisfies the three properties, right? The order of U and V doesn't matter. It's you can easily check that it's linear. And if you take the inner product of U with itself, you get something non-negative in this case. So this satisfies all three properties. This is a valid inner product that's not equal to the dot product. So there are actually many choices of inner products on a given space. So some people have questions. Yeah, please ask questions.
Yeah, I was wondering about like orthogonality with different inner product spaces. If two vectors are like two vectors in R3 say are orthogonal in one inner product space, are they orthogonal in like all inner product spaces?
It's a great question. So yeah, this notion of orthogonality is really orthogonal with respect to that inner product, right? So now you're asking, does orthogonality with respect to one inner product imply with respect to another? Let's check. So it's a great question. So let's look at an example. So again, okay, just to clarify, let's give these names. Let's call this inner product sub 1, and let's call this inner product sub 2. Okay. So now, so let's pick two vectors that are orthogonal in R3 with respect to the first inner product. So I'm going to choose these vectors, right? So let's say U equals 1, 1, V equals 1, minus 1. Well, the standard dot product of these, this is in R2. Okay, fine. Okay, I guess I need the third coordinate, fine. So the standard dot product of these is 0, right? That's 1 minus 1, which is 0. So they're orthogonal, right? But what about if I take the other inner product? Well, I get 1 minus 2 plus 0, which is minus 1, which is not 0. So it's not orthogonal. So the orthogonality depends on the choice of inner product.
I have a question.
Yeah.
So you just showed us that UV using the second inner product example equals -1, but
Yeah.
doesn't the property of the inner product say that it has to be greater than or equal to 0?
No, because that is only for U inner product U, not for U inner product
Oh,
V. So these are the same vector.
Okay, oh, my bad. I read that wrong.
So are we just like kind of changing the definition of orthogonal? Because wasn't our definition previously like just for dot product?
Yeah, we're generalizing it. We're not changing it. We're saying that now sometimes it's going to be useful to look at different definitions of orthogonality.
Okay.
Okay. Now this second kind of example is actually not the kind I'm going to emphasize in the course. The really important example is the next one. Example 3. So let's let V be the be C11, C minus 1, 1. This is the vector space of functions from the interval minus 1, 1 to R, which are continuous. That's a legit vector space. You can add and scale or multiply those, right? And now, okay, so what are some? So now we're going to define an inner product. Let's define the inner product of two functions f and g to be the integral from minus 1 to 1 of f of x, g of x, dx. Okay, now that's a little bit different from what we've seen before, right? It really is not like the dot product. It's an integral. Now, nonetheless, it satisfies all the properties. Let's check, right? So let's check the first property. Well, the first property is that f inner product g should be, so this is f x gx dx. And I want to check that this is equal to g inner product f. So what do I do?
You check if you can add and scale or multiply.
No, I'm just something even simpler. I'm just going to use the fact that this integral doesn't change if I swap the order. So that was property number 1, right? There are 4 properties, remember. There are 4 properties. One is just that the order doesn't matter, symmetry. But now you do have to, indeed, you have to check add and scale or multiply. So let's check f1 plus f2 inner product g. So this is integral of f1 of x plus f2 of x gx dx. So I want to check whether this is equal to f1 inner product g plus f2 inner product g. What would I do? What's the next step?
Just expand it and then see if it's like equal to that.
Yeah, so now I'm going to use a property of integrals, which is you can split this into 2 integrals. That's a property of integration, actually. And that's what makes this work, that integration has the right properties. And that is indeed f1 inner product g plus f2 inner product g. So I've checked these first 2 properties. And 3 and 4 I won't do now, but they're similarly easy. You can leave these as homework. So that's a legit inner product. So just to make this concrete, let's look at a few examples. So here are some vectors in this. What? Okay, my phone is like listening to me again. This is, or actually somebody's Google Home is here. Anyway, sorry. Okay. But let's look at some functions in this vector space. So f1, let's look at the function x. f1 of x is just x. That's a legitimate function. Let's compute its norm. So norm of f1 squared is f1 inner product f1, which is now an integral. So minus 1 to 1, x times x dx, which is, I guess, integral of x squared, that's x cubed over 3, 1 minus 1, which is, I guess, 2/3. So then, in particular, the norm of this vector f1 is square root 2 over 3. So any questions about that computation? Okay, so get another vector in the space, f2 of x. This is going to be the function x squared. Now this it's a continuous function on the interval. That's all that's required here. Let's compute its norm. Well, this is going to be integral x squared dx minus 1 to 1. That's integral of x to the 4, which is x to the 5 over 5, 1 minus 1, which is 2 over 5. And so then the norm of this vector is square root 2 over 5. And let's compute the inner product between them. Well, this is integral minus 1 to 1 x times x squared dx, which is integral of x cubed, which is x to the 4 over 4, 1 minus 1. And now you see the cancellation. This is 1 over 4 minus 1 over 4, which is 0. So what that means is that these vectors are orthogonal. And the point of this is that this introduces geometry into a situation where geometry was not present before, right? So there's a geometric picture associated with this. And the picture is that, well, there's, you have these vectors of different lengths. So, you have f1 and you have f2. They have these lengths, which are like this length is square root, I guess, 2 over 3. And the other one is square root 5 over 3. And these are orthogonal. And I mean, somehow ultimately the punchline is that everything we did here, all this stuff on the first slide, all this stuff, this still works the same way in general inner product spaces. So you can look at subspaces, you can look at projections, the projection formula works, Pythagoras theorem works, so you have Pythagoras theorem, right? Or I guess x, and we're using x for a variable in some examples. So try to be, this still works. The projection formula still works. All this stuff still works. So the point is that everything we learned actually works in this setting, which really includes some new objects that we didn't look at earlier. And this will turn out to be very useful. So I'll now show you the key application of this. But any questions about this example?
Professor, I'm wondering, what does the -1, 1 mean? Like, what's that constraint right there?
Well, so the -1, 1 makes sense because my vector space is functions defined on this interval, right? So that's why it makes sense to integrate from -1 to 1 because the function is defined on that interval.
I see. Thank you.
I mean, it's one of those things where I could have defined some other vector space and then the limits would have been different. But for this one, this is the natural thing to look at.
Okay, thank you.
Professor, you said that orthogonality depends just on the inner product.
Yeah.
But so would you be unable to say that like f1 and f2 are orthogonal in the vector space V? Does it depend on just the inner product and not the inner product space?
Sorry, it depends on the whole inner product space. So you couldn't even talk about the inner product without the vector space. So when I say it depends on the inner product, I mean it depends on the vector space and the inner product.
So f1 and f2 are orthogonal in V then?
Yeah, in this with respect to, I mean, if you want to be totally pedantic, you'd say with respect to this inner product.
Gotcha. Okay, thanks.
But indeed, if I change the inner product, they may no longer be orthogonal, right? Any other question about this? Okay, you can ask. Some people raise a hand.
Oh, well, I'm not sure I understand the difference between an inner product and an inner product space. So is the inner product space the like where the inner product's vectors lie?
No, an inner product space is literally a vector space and an inner product. That's all.
But an inner.
So the inner product is the function. The vector space is the underlying vector space. And inner product space, that terminology refers to the pair, to both of them.
Okay.
Yep. Any other?
So is the inner product space the set of vectors that satisfy that specific inner product?
No, the inner product space is literally a vector space and an inner product. I mean, you can say a vector space. I mean, yeah, it really is what it says in this definition. It's a pair of things. It's a vector space equipped with an inner product. Any other question?
So not all the vectors in the vector space have to satisfy the inner product?
Oh, no, they do. Because remember, an inner product has to satisfy these properties for every vector in the vector space, right?
Oh,
so,
right.
Yeah. Yeah. Anything else? Okay, so let me now move on to the most important example of this, which is Fourier series. So let me first put some context before telling you how this is related to inner product spaces. So you may recall Taylor series, right? So, if you have a function f, then if it's differentiable enough times, you can expand it like this, right? Now, this is a super useful and important thing. And at a high level, what does it let you do? Well, so it's a series. So the series, well, first of all, it converges under some suitable condition, under some suitable conditions. And what you probably learned in calculus is if you look at the first few terms, you can interpret this as approximating a function by a polynomial, right? So this approximates the function f by polynomials near the point x equals a, right? So sometimes the Taylor series converges everywhere, but sometimes it only works near a specific point, right? It doesn't actually work for all x. And this as you can see from the expression, this requires f to be pretty nice. By nice, I mean infinitely differentiable. If you can't take derivatives infinitely many times, then you can't do anything, right? So now, this, while very useful, is not always adequate because there are a lot of functions that come up in math and especially in physics that are not differentiable, for example, and you still want to approximate them by some nice functions. And sometimes you want an approximation that holds more than just near a point. So in math, there are really the two most important kinds of series are Taylor series, and the second one is called Fourier series. So what is a Fourier series? The idea is, so given a function on an interval, which traditionally is taken to be minus pi to pi for reasons that will become clear in a moment. You want to approximate f by a sum of sines and cosines. So not polynomials, right? So this is a 1.1 of contrast from. And you don't want it'll only work near x. You want it to work on the whole interval. Okay, so when when you ask this, it sounds like it's impossible, right? That's not clear why you should be able to approximate it some arbitrary function by sum of sines and cosines. But this is indeed possible in some very great generality. And just looking ahead, I'll give you an example of something of a Fourier series. Here's one example. The function's absolute value of x. So first of all, this is not even differentiable, right? This is a rough function. Not differentiable. Nonetheless, it has an expansion on this interval minus pi to pi, which is the following. It's equal to a half minus 4 over pi cosine x plus 1 over 9 cosine 3x plus 1 over 25 cosine 5x. And this is an infinite series. So of course, I haven't told you why this is true. We'll see that later. But this is an example of a Fourier series. So it's instead of expressing a function as a series where the terms are polynomials, it's expressing it as a series where the terms are sines and cosines. In this case, just cosines. And it's the main difference. The way I think of it is that this works for functions that are not so nice. It works on the whole interval. So those are pluses when compared to Taylor series. And yeah, we'll see that there are some minuses as well. Anyway, this is just an example. Any questions about what I said so far? So to draw a graph, what this is doing is it's saying that you have this function absolute value of x that looks like this. And I'm somehow writing it as a sum of, the function 1/2, which is, I guess, a function that looks like this, plus, some multiples of the function cosine x. So that looks like plus cosine 3x. So that looks like it just oscillates a little bit faster. ... And this picture looks kind of like it shouldn't make sense, right? The thing on the left is not even differentiable. But it does, and we'll talk about how in a moment. So let me now explain how this works in the case of inner product spaces. So the inner product space that we use in this theory is the following. So this is the one that contains enough interesting examples for which everything still works nicely. So to define it, I'm going to define a new notion. So a function f on, let's say, this interval is piecewise continuous if is continuous at all but finitely many points. In this interval. So you all know what continuous means. The function can be, discontinuous or continuous at any x, and piecewise continuous means it's only discontinuous at finitely many points. So there's some finite number of points in this interval where it's discontinuous. Everywhere else it's continuous. Okay. Now, actually, we'll say we'll add one more constraint to this. Or no, that's fine. This is the definition of piecewise continuous. Any questions about the definition? So, okay, for example, the step function s of x equal to 1 for x in 0 to pi, 0 for x equal to 0, and -1 for x in minus pi to 0. So it looks like this. So it's -1 over here, 0 over here, and then 1 over here. This is a piecewise continuous function on this. Let's say this is minus pi to pi, because there's one point where it's not continuous, namely 0. Okay, somebody asked a question. Could you ask it by speaking?
Oh yeah, so wouldn't that mean that as long as it's defined somewhere on a closed interval, then it's piecewise continuous?
No, so there you can define functions that are discontinuous at infinitely many points.
But if it was on a closed interval, then wouldn't it have to be finite?
No, it wouldn't. So for example, so non-example, f of x equals 1 if x is rational, 0 otherwise. That's a legitimate function, right, on the interval, but that's not continuous anywhere.
Okay, thank you.
So we won't be dealing with such pathological functions in the course, but it's a great question. Okay, so we've defined piecewise continuous functions, and now we're going to define an inner product space. So definition, let V sub pi be the vector space of piecewise continuous functions on this interval. And bounded. So bounded means does not go to infinity. Okay, it doesn't mean anything fancy. It doesn't go to infinity anywhere on the interval. Now that is a vector space. Okay, if you take two functions like that and add them, you get something else that's piecewise continuous and bounded. And if you scalar multiply it, that's still preserved. And now we'll define an inner product on this. The inner product will be the same as the one before, except for minus pi to pi. Now, you might ask, why have we thrown in these piecewise continuous and bounded conditions? Well, it's so that this integral makes sense, right? So if you go back to calculus, if you have a piecewise continuous and bounded function, you can always integrate it. And in fact, a product of two such functions is also piecewise continuous and bounded. So that's why this integral is always finite, right? And that's why we need these technical conditions. Otherwise, you don't want to have integrals that blow up and stuff like that. Otherwise, it wouldn't be an inner product, right? It has to give you a real number for every pair of vectors. So this is an inner product space. And what are some functions in this space? Excuse me? Did somebody have a question? Okay. So what are some vectors in this inner product space? Well, okay, sine x is there. That's actually continuous. sine nx is there for every integer n. Cosine nx is there for every integer n. The function 1 is in there, right? 1 is a function of x. The step function I wrote above is in there. This example, right? This is a step function. Because piecewise continuous and bounded. The absolute value function is in there, which was mentioned earlier. And there's a ton of stuff in there. We'll see some of it later, and you'll see even more of it on the homework. And all linear combinations of these things are in there too.
Isn't sine x and cosine x, aren't they continuous, not piecewise continuous?
Yeah, so every continuous function is also piecewise continuous, right? Because the finitely many could be 0, right? So this includes continuous functions.
Okay. And also, sorry, but could you explain again why that's a non-example? The 1 if x is rational and 0 otherwise?
That is a bit beyond the scope of this course. Yeah, I don't know if everybody even. I mean, we'd have to get into the definition of a derivative and so on.
Okay.
It's basically because the limit, the derivative is defined as a certain limit, and that limit doesn't exist anywhere. But proving that is a little bit maybe beyond the scope of this course. So, but if you take Math 104, you'll learn why, and you can intuitively see why, right? Like that function just you can't even visualize it; it just like jumps around everywhere. So, yeah. Okay. So this is our inner product space. And it contains, for example, these vectors. So any questions so far? Okay, so the reason is that the integral exists and is finite by these properties, by piecewise continuous and bounded property. You can review your Riemann integral that you learned in calculus to remind yourself of why that's the case. Okay, so now let's look at some interesting subspaces of this space. Okay, so here's the definition. A function f in v pi is even if f of x equals f of minus x for every x. Oh, sorry, it's not a vector, it's just a point. For every x in minus pi. So that's just a way of saying if you reflect the function across the y-axis, it doesn't change. Right. So for example, absolute value is an even function, right? It looks like this. And the function is odd if the opposite happens. If you look at f of minus x, you get minus f of x for every x in minus pi to pi. An example of a function like that is x cubed, or actually even just the function x, right? When you flip it across the y-axis, it gets flipped, right? So those are even and odd functions, and it's kind of a simple exercise to see that these are both subspaces. So let v pi sub even be the set of functions, even functions, Okay. So these are both subspaces of VPy. By the way, anybody have an idea what the dimension of VPy is?
Is it infinite?
It's infinite, yeah. Why is it infinite?
Because there's an infinite number of functions that can like satisfy that, or I guess infinite number of linearly independent functions that satisfy that definition.
That's right. For example?
Just a bunch of polynomials.
Yeah, this is infinite dimensional because it contains infinitely many linearly independent vectors. For example, the polynomials. So 1, x, x squared, dot, dot, dot. So that's an infinite dimensional vector space. These are also infinite dimensional. You can convince yourself of that later, but nonetheless, they're legitimate subspaces. And the reason we're interested in these is that they actually turn out to be orthogonal complement of each other. So that one is they turn out to be orthogonal complement of each other with respect to that inner product. So let me write down these sort of easy plus useful properties. So the first one is that the integral from minus pi to pi of an odd function is 0. Sorry, or just say if f is odd. Now, okay, why is that? Well, okay, let me just write the proof actually. Well, okay, so now you split this in two integrals, right? So you have minus pi to 0 f of x dx plus integral 0 to pi f of x dx. But now you flip the integral, right? So if I flip this integral, I go from, well, let's see, what order do I want to do this in? You know what, rather than doing a formal, let me just draw a picture that will convince you. So if you have an odd function, let's say this function, these two integrals, so one of them is computing this area, but because when you flip it across the y-axis, you get the negative mirror image, right? So the first integral is computing this area, but with a negative sign. And so these cancel, and you just get 0. Formally, you do a little change of variables, x equals minus, u equals minus x or something like that, but yeah. So for an odd function, its integral on this interval is just 0 by symmetry. The part on the positive x-axis cancels the part on the negative. Okay. By the way, another important example of an odd function is the function sine of nx, right? Because sine of minus x is minus sine of x. That means that's an odd function. So integral of sine nx on this interval is always 0 as well. Okay. Now this implies two other kind of neat properties, which is if you take an odd function and take its inner product with an even function, well, or actually forget the inner product. Let's just write if the product of an odd function and an even function is, so do you think it's even or odd or neither? By the way, functions don't have to be either of these things. Do you think it's even, odd, or neither?
Odd.
Odd. Yeah. So why? Well, if you just plug in minus x here, then the even x doesn't get affected, but the odd x flips sign, so the product flip sign. Another nice property is if you take odd product of two odd functions, what will that be? Well, that's even. This is why they're called odd and even, because they behave like numbers. And then finally, the product of two even functions is also even. Okay, so we're going to use these a lot in calculating inner products in a moment. But any questions about these properties? I mean, important remark, by the way, not all functions are either even or odd, right? Functions could be neither. Okay, this is an important, sometimes people make this mistake. They're thinking like numbers, every function must be even or odd, but that's not true. For example, absolute value of x plus x, that's not even or odd. Okay, so now armed with these properties, we're going to make a really crucial observation. But any questions? Yep.
Is 0 the only odd and even function?
That is it. Yeah, 0 is the only odd and even function. Correct. That's right. I leave that as an exercise. Although what we're going to do in the next slide will kind of prove it. But okay. So what's one consequence of this? The consequence is that if f is in the even subspace and g is in the odd subspace, then what's the inner product? Well, it's this. But f is even, g is odd, so f times g is odd, right? This product is odd. So what's this integral?
0.
0 by the first property. So these subspaces are orthogonal to each other under this inner product. And okay, you can actually prove one is the orthogonal complement of the other. So okay, so now let's build on this picture here. So we have this picture that well, okay. So let me write the key observation behind the picture. So the key observation that I want to make is that this set of vectors, 1 cosine x, cosine 2x, dot dot dot, sine x, sine 2x, dot dot dot. So it's an infinite set. So sometimes we write that in this notation that this is cosine nx, the function's cosine nx, union index from n equals 0 to infinity, union function sine nx, and goes from 0 to infinity. Key observation is this is an orthonormal set. In the inner product space V pi. No, sorry, orthogonal, not orthonormal. Okay. So let's prove that. It's a very important observation. Well, what's an orthogonal set? Well, it means that if you take two vectors in the set, their inner product has to be 0 if they're different, right? So let's compute some inner products. So by the way, 1 is just equal to cosine 0x. It's just equal to cosine 0x. That's why I've clubbed it in with the cosines. So what's the proof? Well, let's compute some inner product. So what happens if you compute an inner product of a cosine and a sine?
Would it be 0? Because cosine is an even function and sine is an odd function?
Exactly, yeah. So if m and n are any integers, then this inner product is 0 because exactly of what Vindhya said, this is an even function and this is an odd function. So no integration necessary. We know this. Okay, so mutually, all sines are orthogonal to all cosines. But what about two different cosines? Well, so m and n are integers now, right? Well, now we actually have to do some integration, right? So this is integral from minus pi to pi of cosine nx, cosine mx dx. Anybody have an idea how to attack that integral? It's a calculus question.
Is there some property that, like if you have cosine A, cosine B, can you combine that to make some property? Or
Yeah,
maybe
that's right. There's this sum product formula, which you may remember. I had actually forgotten it until I prepared this lecture, but there's this formula that allows you to express a product of cosines as a sum of cosines. And what it says is that this is cosine m plus n times x plus cosine n minus m times x dx. So this is a trig identity, which maybe you remember. Okay. And now, okay, what ends up happening here is it really depends on m and n. So there are three possible things that can happen. The first is it's equal to 0 if m is not equal to n. Now, why is that? Well, when m is not equal to n, right, so m and n are, sorry, not just m and n are non-negative integers, right? So maybe I should. So if m is not equal to n, then m plus n is not 0, and m minus n is also not 0, right? So both of these integrals become integral of cosine kx for some k. And this is just 0 when k is not 0. You can just do the integration. I will not bore you with it here. Okay, so if m is different from n, this is 0. So any questions about that case?
Would k only be 0 if m equal to n?
That's right. So that's the next the next case. So the next case, there are actually two more cases. So it's equal to pi if m is equal to n, but they're both not equal to 0. And in that case, what happens is that if you look at these terms, this term becomes cosine 0x, which is 1, and this term just remains cosine kx, right? So in that case, one of the terms vanishes and the other one just becomes 1. And this is since integral minus pi to pi 1 dx equals pi. Sorry, equals 2 pi, and there's a half in front of the whole thing. right? So we're just paying attention to these two green terms. And then finally, the last case is it's 2 pi if m equals n equals 0. Again, for the same reason, but now both the terms are equal to are equal to cosine 0x, right? If m and n are both 0. And so you get twice. So this is a little trig, calculus exercise, but it actually proves essentially the key observation, or at least half of it, which is that these vectors, the cosines are pairwise orthogonal, right? The first property means if m is not equal to n, they're orthogonal, right? So this means this property says that they're orthogonal for m not equal to n, and the last property says it actually tells you what the m equals n means. You're calculating the norm, right? So it tells you that norm of cosine nx squared equals pi if n not equal to 0 and 2 pi otherwise. So this, in linear algebra terms, this little calculation is telling us that these actually are an orthonormal set. So any questions about that?
You said that like the integral for an odd function is 0, but like cosine nx is an even function. How can it be 0 when k is not equal to 0?
Oh no, it can be 0. So I didn't say integral 0 if and only if the function is odd, right? I said odd means the integral is 0, but it could also be 0 otherwise.
Okay, all right.
So this, I mean, okay, so this is also calculus. Maybe, I don't know if you remember doing that recently. I just skipped. You have to do the integral, but you see that it's 0.
All right, thank you.
Yep.
Could you repeat again how the 2 pi, like why is there a half in front of the second condition when m equals n? How did the 2 pi become pi?
Oh, because there's a half in front of the whole integral.
Oh, okay.
Yeah. And then similarly, you do the same thing for sine. I won't repeat it. Sine nx, sine mx equals, here there are only two cases, equals 0 if m not equal to n, and equals pi if m equal to n. They can't be equal to 0. Sorry, yeah, I should correct this. In the sine case, you go from 1 to infinity. Sine of 0 is just a 0 function, so we're excluding that. So this is similarly. Okay, so the proof is just, it's a little trig integral. But what is the picture that emerged from this proof? So let me summarize this in a picture. But any questions before I proceed? Okay, so the summary is that this vector space V pi actually looks like two orthogonal subspaces, the even functions and the odd functions. And inside these subspaces, we have some interesting orthonormal sets. So in here we have this orthonormal set of cosines. So I guess starting with 1, but cosine 2x, etc. It's infinite. So there's a new twist, right? Infinite orthonormal set, something we haven't seen before. And in here we have another infinite orthonormal set of sines. Okay. And these are also orthogonal to each other. So they form an orthogonal set in the whole vector space. And then we have some other example functions sitting around in here. So the one even function that's sitting in here is the absolute value function. An odd function that's sitting in here is the step function. We have a few other examples in these vector spaces. And okay, and the norms of these things are some kind of funny multiples of pi. as shown here. So they're not orthonormal, they're orthogonal bases. But now what do you know about orthogonal bases? Well, you know that these sets are linearly independent, right? You know that any set of sines or cosines is going to be linearly independent, right? Because these are non-zero and orthogonal. Right? Going back to chapter 6, non-zero orthogonal set are linearly independent. Now, that's interesting because now that means we can try to think of expanding functions as linear combinations of these orthogonal sets, right? So, namely sines and cosines. So we haven't proven that there are bases yet. I mean, we'll get to that later, but we can still try to expand, right? So let me ask this question. So here's a sort of interesting question. If you have some function that's a linear combination, I'm going to write it in this funny looking way. So a naught over 2 times this plus n goes from 1 to k, a n cosine nx plus b n sine nx. So this is a good old finite linear combination. How do you find the coefficients a naught over 2, a1, a2, b1, b2, dot, dot, dot. Any ideas? So I just told you that they're an orthogonal set. And I suppose I know some function is a linear combination of them. How would I find the coefficients?
Put them in a matrix and solve the system of equations.
Okay, so you said put them in a matrix. Well, you can't, right? Because they're infinite dimensional vectors, right? How are you going to put cosine nx in a matrix? You can't put that as a column of a matrix.
I think you can take the inner product, or yeah, the inner products of like a naught over 2, and then everything else should cancel out, and because it'll go to 0. And then
Yeah, exactly. So we're going to use the same trick from chapter 6. Let's say I want a naught over 2. Well, I'm just going to take the inner product of this thing with 1, right? So now I have this whole sum. Sorry. And this is where the inner product comes in. It works exactly the same way as a dot product, right? So by linearity, I can isolate the terms. I get a naught over 2, 1 inner product. Sorry, not f. What am I doing? Sorry. Okay. Okay. I flipped the order, but I can do that because it's an inner product. Or okay, fine. Just to be consistent, I won't flip the order. I'll put a 1 here. And then, okay, so this becomes a naught over 2 times 1 inner product 1 plus the rest. Oh, sorry, I keep writing it in the wrong order. 1 inner product that. Or let me pull the an out as well. And now the nice thing that happens is these go to 0. Why do these go to 0?
You're orthogonal.
They're orthogonal, yeah. Same reason as before in chapter 6, what we wrote above, right? By orthogonality. So you get that these coefficients, so a naught over 2 is equal to 1 inner product f over 1 inner product 1. And similarly, you get an is equal to cosine nx inner product f over cosine nx inner product cosine nx. And you get bn is equal to the same thing for sine. And these should look very familiar. These are literally the same formulas you used in chapter 6, but now in these infinite dimensional spaces. So that leads us to the definition of Fourier series, which is we're going to define a series with these numbers as coefficients. You know, that's what it would be if these vectors were an orthonormal, infinite orthonormal basis. So let's get to the definition of Fourier series. So any questions so far?
I'm a little confused about how we know the dimension. Like, how do we know how many coefficients are there?
We don't. So here I just said if you know f is only with k coefficients, then this works, right? Sorry, you're right. So I should have said for n going from 1 to k. I haven't got to infinite dimensions yet. You're right. So this is if I know f is a linear combination of some k sines and cosines, then this will work.
Okay.
But now I'm going to make a leap of faith and just define the same thing for infinite linear combinations. It's the first time in the course we see infinite linear combinations. So here's the definition. If f is a function in this vector space, its Fourier series is defined as, I'm going to call it fs sub f of x. And the definition is it's the following series a naught over 2 plus, summation n goes from 1 to infinity, an cosine nx plus bn sine nx, where these are defined exactly as they would be if the projection formula worked, and exactly as they were for finite linear combinations. So a naught over 2 is 1 inner product f over 1 inner product 1, which, you know, so I always get confused about the 2's here, which is 1 over pi integral minus pi to pi f of x dx. Now, okay, so what happened to the 2 here? Sorry, 1 over 2 pi, yeah. And the reason for this 2 is just a sort of historical artifact that we end up wanting the same formula for a naught and an. So what's the formula for an? Well, it's cosine nx inner product f over cosine nx inner product cosine nx. Now we calculated that a few slides ago, right? Cosine nx inner product itself is just pi if n is not 0, right? So this just becomes 1 over pi times integral minus pi and pi f of x cosine nx dx, and bn is equal to the same but for sine. Sorry, sine here. Okay, so these are called the Fourier coefficients. Okay, and you know what I'm trying to convey is that it's a fancy word, but we're going to see that they're just coefficients in this infinite orthogonal basis. It's just the projection formula, but in infinite dimensions. So maybe this will look better if I do an example. So let me do an example. Let me do the function that I started with, the step function. So yeah, so we have this step function S of X. On this interval. So what are the Fourier coefficients? Well, a naught. So by the way, first question, is this function even or odd or neither?
Odd.
It's odd. So the so a naught. So by the way, a naught is okay. I mean, it has a formula, right? Well, that's just going to be 0, right? We don't have to even have to do the computation because it's odd. So if it's odd, all the cosine coefficients are 0. Because this is odd. So no computation required. This is why I told you about even and odd, because it saves you a lot of work. And it also, I mean, it comes up again and again conceptually. Now, you're going to have to do something interesting for the sine coefficients. So this is 1 over pi, some integral, minus pi to pi. So now you'll have sx sine nx dx. And now you have to do some integration. Okay, so this is 1 over pi. You can split the integral into 2. Integral, I guess, minus pi to 0 of minus 1 sine nx dx plus integral 0 to pi 1 sine nx dx. And now, okay, if you flip the integral and cancel the minus signs, you see that these two are actually the same. So you get 2 over pi integral from 0 to pi of just sine nx dx. And now you have to do that integral. Anybody know how to do that integral? Anybody do these integrals in calculus?
You're just going to get 1 over n times negative cosine of nx from evaluated at pi and 0.
Yeah. So this is not a complicated integral. It's just 2 over pi. So you get cosine nx over n negative evaluated at pi and 0, which is, you can check. So this is 0 if n is even, because cosine even number times pi. Oh, have I got this backwards? Wait. Yeah, cosine even number times pi is 1. Okay, fine. Let's just write out what this is. So this is minus 2 over pi n cosine n pi minus cosine 0. Yeah, and now the point is that, yeah, so if n is even, this is 1 minus 1, which is 0. And if n is odd, it's actually minus 2. So it's 4 over pi n if n is odd. So what that means is that the Fourier series of this function, the step function, is the following series. So the a terms are 0. The sine terms are there. So it's 4 over pi times sine x over 1 plus sine 3x over 3 plus sine 5x over 5 dot dot dot. And that's the Fourier series. Now that's how to compute it. But the miracle is that the Fourier series of function is equal to the function for, well, okay. I mean, we'll do this in detail next time. Almost everywhere. I mean, okay, I don't want to say that, but so Yeah, let me just put this in quotes. And so what that means is that this orthogonal set actually behaves like an orthogonal basis of V pi. Okay. For all f in V pi. And so these sines and cosines behaves like an infinite orthogonal basis of this vector, of this inner product space. Yeah, so anyway, next time I'll tell you in what sense that's true, and I'll tell you some really cool applications of this, but that's the intro to Fourier series. Any questions?
Yeah, can we go back a slide?
Sure.
When we said that an odd function has an integral, or like when we integrate an odd function, it's just 0.
Mm-hmm.
Is that because we're taking our integral from like minus n to n?
Minus pi to pi.
Oh, yeah.
So, right, because, yeah, this is minus pi, this is pi, and you get this exact cancellation between the positive part and the negative part.
Okay, so
mm-hmm.
so then, like, I think 2 slides after this, yeah, actually 1 slide before this, we had sine going from 0 to or 1 to infinity. I don't know if this was the slide. Yeah, sine was going from 1 to infinity, and we said that it's equal to 0.
Okay, good. So I think the confusion here is that this n is, I'm not letting x go to infinity, right? X is the variable that's in minus pi to pi. N is this like index 1, 2, 3, 4, 5. It's an integer.
Oh, so we're taking the integral from 0 or minus pi to pi, but the n is going from.
Yeah, so I'm using this notation to specify an infinite collection of vectors. So maybe this is a new notation for many people, but you know, this n in this subscript is an integer.
Okay.
So I'm just using, this is just shorthand notation for what's written in the first line, right? There's an infinite set of cosines and sines.
Okay, yeah, that makes sense.
Yep.
Professor, another question on this slide.
Mm-hmm.
For the 0 line, how do we conclude that cosine kx, that integral is equal to 0 if cosine is an even function?
You have to actually do the calculus, right? So the integral of cosine kx is sine kx over k. Evaluate that at pi and minus pi, you'll see that you get 0.
Okay, cool. Thank you.
Yep.
Professor, so for the line right next to the proof on this slide, I'm a bit confused because like this is like an inner product, right? Cosine nx, sine nx, or sine mx.
Yeah.
So is it for like, because I don't know, because isn't an inner product, it can be like any function. So is it for any function that you plug in?
Well, it's for these very specific functions, right? Cosine nx and sine mx. But yeah, m and n can be anything.
Right, but
So let's see. So the inner product being used is the one written over here. So you know the key inner product is this definition.
Okay.
And now when I literally compute that inner product of cosine and sine, I have to do the integral, but I skip doing the integral because I observed that one of them is even and the other is odd. And I observed that even times odd function is odd and integral of odd function is 0.
When the bounds are like from the negative n to n.
No, from negative pi to pi. So I think, yeah, so similar to what Vindhya was saying, I think there's some confusion about n and x, right? So n is telling me which cosine function I'm looking at. Cosine 1x, cosine 2x, cosine 3x, etc., etc. X is actually the variable in the function.
Okay, yeah, okay, maybe n was the wrong letter to use, but if you go back to the graph that you just showed where like wouldn't it doesn't it not matter if it's pi or like 1,000 or whatever, like as long as they're both the same on each side?
Absolutely.
Yeah.
It doesn't matter as long as they're the same on each side. But
Yeah.
in this case, we're never integrating from minus n to n. That just doesn't come up because n is being used to say which
Sorry,
frequency of sine or cosine.
that's a not great letter to choose. Okay, so I think I just missed the part where we defined the inner product as that specific integral.
Yeah. So it's this specific integral, and these specific limits of integration are important. And specifically for this even and odd thing, as you noticed, what's important is that it's minus pi and pi, so they're symmetric.
Yeah.
That's why the cancellation happens.
Okay.
If it had been like 0 and pi, that wouldn't have happened, right?
Yeah. Okay, cool.
Professor?
Hi, Professor. Is the homework from this week during Dead Week, or is it part of homework 12?
No. This is during Dead Week.
Okay. Yeah. So, okay, great. Thank you.
So we're following the same rule. Last week's homework is due this week. Yeah.
Okay, great. Thank you.
Professor, I was just wondering why you use 1 when you take the inner product. I think it's on the next slide or 2 slides after this.
Here?
Yeah. Why do you choose 1 there?
Oh, 1 is, it's just the first function in the series, right? In the sequence, it's cosine of 0x.
Do you have to use 1 or could you use something else?
I mean, in this example, you could use any, this reasoning works for any, you could throw in any linear combination of cosines and sines here, and this type of reasoning would work. It's just, I mean, it makes sense to order them with increasing n, right? And so that's why we start with 1, because it's the lowest one, cosine 0x.
And then it cancels because then it's an odd function.
Yeah, it cancels because it's an odd function, or more at a higher level, it cancels because of orthogonality, right? We already established that these are an orthogonal set. So you take any 2 of these functions, their inner product is 0, and that's what we're using here, right? Because 1 and cosine nx and 1 and sine nx are pairs of orthogonal functions. So their inner products are 0.
Okay, that makes much more sense.
Yep.
Thank you.
Professor, when you say like sine x and cosine x behave like an orthogonal basis, does that mean that they're actually not a base?
Yeah, so the reason I put it in quotes is I have not defined what an infinite linear combination is, nor have I defined what an infinite basis is.
Oh, okay, yeah.
Right, so linear combinations are always finite in this course, and so that's why I put it in quotes. Next semester, next lecture, I'll make a rigorous statement about what I mean by this.
Okay, yeah, thank you. And can you go back to the definition of the inner product space, I guess?
Sure.
Okay, so I guess like an inner product space is like a vector space plus an inner product, but like I mean, like, what if a same vector space has like different inner product? Does that count as different inner product space or the same?
Yeah, different inner product space.
Oh, okay,
so
thank you.
For example, in example 1 and example 2, you could have R3 with these two different inner products. Those are different inner product spaces.
Oh, yeah. Thank you.
Yep.
Professor, could you go to the slide with the Fourier series definition? Yeah, this one. Thank you.
Yep.
Have a nice day.
Yep, you too.
Professor, why did we decide to go from negative pi to pi of all numbers?
Because sine and cosine are really easy to evaluate at those numbers.
Oh, so this whole thing would have worked even if we chose, like, I don't know, negative pi over 2?
It would work for any negative L and L, and I'll make a remark about that in the next lecture. You just have to look at some rescaled versions of sine and cosine in order to make these cancellations easy, because we really did use pi here, right? Like cosine kx is 0 because we went from minus pi to pi. It's not 0 if you go from -1 to 1, for example.
Yeah. So So because these properties are really nice, that's why we chose negative.
Yeah, that's right. Because pi and minus pi are really special for sines and cosines, right?
Yeah. Okay.
If you had a vertical asymptote, could something be piecewise continuous?
It could, well, it could, according to this definition, because it would only be discontinuous at the vertical asymptote. But remember, in our vector space, we said piecewise continuous and bounded.
Oh,
A
yeah.
vertical asymptote is not allowed. That's why we threw that in there. Otherwise, we could have some diverging integral or something, and we would be stuck, right? So yeah,
Yeah.
good question.
Would it work still? Because, you know, with some indefinite integrals or some, or what are they called? Improper integrals, you can
Yeah,
take the limit.
that's
Do
a
they-
great question. So there is a version of this that works for improper integrals, but it's kind of more complicated, and we won't be doing it in this course. But you're right. There are versions of this that work for improper integrals, and they're very important in physics.
Cool. Thank you, Professor.
Yep.
Professor, could I ask a question about logistics?